people have arrived. With that, welcome everybody to today's webinar on the IEA SHC Solar Academy. Today's topic is compact thermal energy storage materials, focusing on better material characterization and determination of material degradation mechanisms. This IEA SHC Solar Academy webinar is hosted by ISIS, the International Solar Energy Society. We are very happy to have all of you here and also happy to welcome our speakers and you, the audience. My name is Melina. I'm from the ISIS headquarters team in Freiburg, Germany, and I will give you a short introduction into ISIS and the work we do. The International Solar Energy Society, ISIS, is a non-profit, UN-accredited membership NGO founded in 1954. ISIS represents a diverse membership of academics, researchers, energy practitioners, consultants, students, businesses, and advocates. Our vision is 100% renewable energy for all, used efficiently and wisely, and we work together with like-minded organizations from countries all over the world to advance the renewable energy transformation. And to advance this mission, we work on several key areas, which are the congresses. We organize 2 major scientific congresses, the ISIS Solar World Congress and Eurosun. Eurosun is taking place in cooperation with IEA SHC on biannual rotation. And the Solar World Congress started in 1970, and this year it will be hosted in Brazil from the 4th to the 7th of November. Call for papers is open until the end of April, and we also do welcome contributions from today's webinar's topic. So feel free to submit your abstracts. And Eurosun conference started in 1996 in Freiburg in Germany. And last year we were in Cyprus. And next year in 26, Eurosun will come back to Freiburg, Germany for its 30th anniversary. So also stay tuned for the call for papers there. ISIS also publishes the Solar Energy Journal since 1957. It is one of the oldest and leading journals in the field. And we have also our latest edition, the Solar Energy Advances, which is a fully open access journal. And we also started offering webinars, and they have become a key activity for the society on a monthly basis. They're free to attend, and we have up to 500 attendees every month. And we are super happy to cooperate with our partner organizations on the webinars, for example, with IEA SHC on the Solar Academy series like today, but we also work with REN21, GWNet, the Global Solar Council, and other organizations. And we also do offer a range of education initiatives to students and young professionals, such as in-core or a master's course during conferences. We have an infographic series, and we also launched an online solar energy museum, which brings together information from solar history, research and development of the last 60 years, and it highlights important renewable energy pioneers, companies, and others that were key for the growth of the solar energy sector. Worth to take a look. And as we are a membership organization, we invite you all to share our vision of renewable energy for all. And to join us as a member, we offer a wide range of membership benefits on all our services. So definitely also worth to take a look. Okay, so now regarding the webinar, a brief information on the Q&A session before we start. For the Q&A, we invite you to send your questions through the Q&A text box that you see, and we are looking forward to your participation. So when sending in the question, you can write the name to who the question is, and please keep it short and precise so that it can be then asked to the speakers. And you can also feel free to start sending in your questions anytime throughout the webinar, and then they will be addressed by our moderator, Bärbel Epp, later in the Q&A session. And with that, I'm also happy to introduce our moderator of today, Bärbel Epp. She is the founder and managing director of the German consultancy Solrico. She is responsible for the international newsletter of Solar Thermal World, reporting exclusively about market and technology trends in the solar heating and cooling sector globally. Bärbel has a background in physics and graduated from the University of Oldenburg in Germany, and she will be today's moderator, and she will give us also a short introduction on the IEA SHC. And now I'm very happy to hand over to you, Bärbel. Thank you for joining us today. The floor is yours.
Yeah, thank you, Melina. Great to have you all with us today for this solar heating and cooling webinar. I will give you a short introduction into what is the IEA Solar Heating and Cooling Program. Yeah, well, it's a quite old research platform which started already in 1997, and it has 20 member countries, the Commission plus 9 international organizations. So all countries which are colored here, either yellow or red, are members of this big group of researchers, around 200, and they are organized in tasks, as we call them, you know, the topics they are working on. So we have PVT, heating and heating systems, we have solar district heating, we have the high comfort integrated lighting systems, solar hot water for 2030. Then the difficult topic and cross topic life cycle and cost assessment for heating and cooling technologies. A new one is solar photoreactors for production of fuels and chemicals. And the one which is responsible for hosting the task today, the webinar today, which is compact thermal energy storage materials. And we all give them numbers. So we have today hosted by the task 67. So what is the Academy doing? They want to spread all the knowledge which is worked on in the different tasks and topics, because we have to stress that it's not only scientific results that are produced, but there are also a lot of training materials available, case studies, fact sheets, databases, and also tools are developed within the program. We hold these quarterly webinars together with ISIS. The next one is foreseen in June 24th and 26th, and they are always taking place twice. So one time in the afternoon, 2 GMT, and one time in the morning hours, 6 GMT, with a rebroadcast, so and a live Q&A. You can also look into the recordings of previous webinars under this link on our website. And importantly, also, we offer on-site trainings on request of IEA SHC member countries and organizations. You see that we are around the world active. There were trainings in China, Cape Verde, which is West Africa, and United Kingdom recently. And now the next one is foreseen in August, 28th to 22nd of August. And the topic is solar drying and industrial cooling in the SADC region, and it will take place in South Africa. Yeah, where do you find more information? There's first our website, ieashc.org. There you have a section which is called Publications, which gives you the latest reports for download. All is available free of charge. Then you have the social media section, LinkedIn. You can follow us on YouTube. And if you have any particular questions, don't hesitate to contact the Secretariat. There are two publications I would like to stress particularly, which is the Solar Heat Worldwide report, which is published once in June every year. It's the most comprehensive data gathering on national market development on solar heating and cooling programs, and also regarding different applications. So you find latest information on solar industrial heat, on PVT, on process heat, and different applications. And the other one, Solar Uptake, is a biannual newsletter, which you also find on the website for download, and which gives you insights into what's happening currently in the different tasks. With this, I already get to our first speaker. We have 3 speakers today, and Wim van Helden is working at the Austrian Institute INTEC since 2014 as a senior expert on thermal energy storage. He has very long experience in leading national and international research and demonstration projects, either with large-scale solar thermal storage or with compact solar thermal storage as today. He's also the task manager of this task 67 that I already mentioned. And he studied technical physics and did his PhD in energy technologies at Eindhoven University in the Netherlands. He is living partly in the Netherlands and in Austria, shifting from one drive to the other. He will give us an insight on IEA SHC task 67 and is talking about advances in materials and performance. Wim, over to you.
Thank you, Bärbel, for this introduction. Yes, about task 67 and also task 40 on compact thermal energy storage materials within components, within systems. That's a mouthful. You will hear in this webinar, especially on the materials research, but also something about the component research. And the idea is that in my presentation, you will hear about, say, the components research and the research on the materials development. First, an introduction to the task itself. It has two names and two numbers also because it's a joint task between two IEA programs. One is the solar heating and cooling program, the present program of today, and the other one is the energy storage program. In the task, more than 60 experts from 14 countries worldwide worked together, and we started in June 21 and ended last September in 24. What is the scope of the work that we did? We say focused on compact thermal energy storage materials, meaning that we paid our attention to phase change materials, PCM, and thermochemical materials, TCM. And on these materials, we did material characterization, material development, material improvement, and also material testing in components. And these main components are heat exchangers for PCMs and reactors for TCM. To the right, you see an example of a very famous PCM, water, changing phases from ice to liquid water. And TCM, zeolite beads here in set up within a dishwasher machine. More about these materials later. So what were the goals that we had with the task? We would like to have a better understanding of those factors that are influencing the storage density and the performance degradation of compact materials. We would like to be able to characterize these materials in a reliable and reproducible manner. And these two goals will be covered by my colleagues Christoph Rathgeber and Daniel Lager later on in this webinar. Another goal is to have methods to effectively determine the state of charge of a CTES and to have better knowledge on how to design optimized heat exchangers and optimized reactors for CTES technologies. Let's first turn to the material development, a few slides on the material development. First, a slide for thermochemical materials. If you look to the bottom, then here are the objectives of the work. Let me have the laser pointer. In the blue square, the objectives for TCM are that we would like to work from understanding of the phenomena to demonstration scale, meaning that we would like to couple the materials level to the say prototype or systems level. Also work on the development of new materials and processes, and to improve different properties of the material, like the storage capacity, the structural stability, the heat and mass transfer, mechanical properties, etc. And the pathways to arrive at these developments are to form composite materials, to work on the synthesis and on the production processes, and to also look at the scale-up effects going from, say, gram to kilogram to ton scale material. The materials studied are inorganic and organic salts, zeolites, and aluminophosphates. And we were also worked on binding these materials in matrices, porous matrices in general, but also ceramic matrices, and also to work with natural adsorbents in the production process. And then different technologies are being applied to improve the quality or the performance of the material, encapsulation of the active material, adding fibers, coating of the material, and also using phase change materials as a matrix for thermochemical materials. On a PCM level, the objectives were to work on new materials and new mixtures, and also improve different properties, thermal properties, thermodynamical properties, mechanical, Also work on the mitigation of subcooling, which is a rather stubborn problem with phase change materials, on the stability of the material and the compatibility. Pathways here is that we again work on composites, on additives and external stimuli. And these additives and external stimuli are for the subcooling mitigation, and on characterization and prediction of performance of the materials. As you see, these are different ways that we walk for PCM, because PCMs are farther developed and more in the market. There is a large number of manufacturers of PCM materials. Therefore, we work on, say, novel advancements for the materials. Materials that we studied are inorganic, salts and salt hydrates and plastic crystals, and inorganic materials like esters, fatty acids, esters, plastic crystals, and paraffins. We work on encapsulations, on adding fibers, on coating, and on shape stabilization. Some examples of materials for modification strategies here in this slide. First, for tailoring the energy density or for tailoring temperatures. One method is, especially with salt hydrates, to work with doping, that materials are doped and that therefore the crystal lattice is changed and therefore the uptake of, say, water vapor or other vapors is increased or decreased. So modifying then the, say, the enthalpy of the material. Another way is functionalization. Here, a PCM material is added with a surface active agent in order to increase or, in this way, to decrease the hydrophility of the material. Also, mixing active materials is possible. Here we have a lattice material of, for instance, a zeolite, in which a salt hydrate can be impregnated in order to make the salt hydrate more stable to prevent the fluidizing of the material. And last but not least, coating, encapsulating solid liquid PCM with a solid PCM, and therefore preventing the liquefaction of the first component. For tailoring heat and mass transfer, different methods are available. The first is to add highly conductive materials in order to increase the heat transfer of the material. The second one is the infiltration or impregnation of highly conductive matrix, for instance, a metal foam with PCM material, or encapsulating PCM with an active or a non-active material, giving shape stabilization to it. These are a few examples of processes and methods that can be used to modify the materials. The outcome of our work is that we have a description of existing strategies to modify material properties, and also a published article on materials improvement case studies. And we have made an overview of expertise that is existing within the group on CTES material improving or optimization. And this is all part of the final report that will be published soon. Then we have on component side, the state of charge determination. Why do we do this? Because for PCM and TCM, the temperature is not always a direct measure for the enthalpy content or of the state of charge of the material, especially if we have a lot of material in a container, if it is a bulk material. The state of charge determination is important for energy system control and for sector coupling. In this case, it is necessary to know what the state of charge is in order to be an active element in the electricity net with power to heat, for instance. And then for this state of charge, there is a search for those physical properties or physical measurable signals that can be connected to the state of charge. So let us see some examples of this, how we worked on this. We have a so-called 3-layer model. The first inner layer is the green part. It's the measurement technique to have material bulk response. So this could be color, this could also be electromagnetic response. And on the second layer, it's an external measurement. So on the storage vessel or on the storage system itself, measuring, for instance, the heat flux or the vessel content itself, in order to have an idea on the total enthalpy incorporated into the system. And on the blue level, it's the system level. And therefore, on this system level, we need the system, we need the state of charge in order to have a better ability to control the system as a whole. Some examples for this are given here. Say in the green material level, work has been done, for instance, by the University of Applied Science in Upper Austria. Here they made an inductive electricity measurement of zeolite beads in the zeolite container. And the inductive signal coming from the zeolite is a bulk measure for the water content and therefore also for the state of charge of the zeolite. So here we have another measurement technique than only the temperature. For the orange, the example here is from the Technical University of Denmark. Here a vessel with a PCM, the heat going in and out of the vessel is measured and monitored. And this heat flux is telling something about the energy content. And if we couple this with a model of the PCM inside the container, then we can calculate what the state of charge is at a given moment. So here the system or the component measurements are used to calibrate at a test stand. And for the system level, here an example is given of work being done in Norway by Sintef. A PCM heat storage here is part of a system in which there is flexibility in the system needed. And the SOC then is giving input into the system control in order to be able to have an optimal control of the system over a longer period. So these were examples of the state of charge work that we did. We also worked on a technology position paper. The idea was that we would generate high-level information as a basis for uptake and further development by different high-level people in industry and in policy. First, we had some description of the current status of phase change and thermochemical materials in the technology position paper. And then we made an assessment of the potential of the technology in different application areas. First, an application area of seasonal storage of solar energy, in which the estimate is that there is a 375 terawatt hours of annual electricity or energy savings possible with this application. Then there's an application already on the market, a dishwasher with zeolite that has energy savings by electricity savings. And if this technology is spread out globally, then the electricity savings would be 4.7 terawatt hours annually. Then the area for distributed power to heat, so small units of power to heat, like the unit being developed and sold by Sunamp in Scotland. For that, we estimated a 300 terawatt hours annual uptake of power from the electricity grid. Data center cooling is one important future application area for compact thermal energy storage materials. Here for the EU, it is estimated that in 2030, there will be 10 gigawatt of demand response available for data center cooling. And then thermal comfort in buildings, which is an area that is widely applied for phase change materials, but through its distributed, how to say, applications, it's hard to make an estimate of the technical potential of this application. And then the last application area is industrial processes. Here, a rough estimate is that 1,600 terawatt hours of fossil fuels can be replaced by using compact thermal energy storage technologies. We also concluded the position paper with a small table of actions needed. Just go through the challenges that we have. One challenge is that the added value to the energy system is not monetized. And this is because storage is always part of an energy system, and we should be more clearly about what the effect is of adding a storage to the complete energy system. Then a challenge is the relatively high cost. This should be overcome by long-term market introduction support programs. Then the challenge of slow progress of the technology development and the technology innovation. This is a challenge that can only be overcome if there's a good targeted support of innovative CTES companies, and that we have national and international programs that are long-term and dedicated, supporting R&D and also aimed at basic CTES materials research. Then the low industry involvement, which is natural because there are no big markets at the moment. And this can be only overcome if there is a targeted demonstration and market introduction support program to avoid the valley of death, which is blocking, say, the step from TRL, say, 7 to TRL 9 for the developments. And a general challenge is that thermal technologies are not seen yet as a big picture by policymakers. We must say that this is moving and this is improving, but it is necessary to increase the awareness among the decision makers and in the broader public on the potential and of the possible impact of compact thermal energy storage technologies in general. So how to go further? As you saw, we ended the activities in September last year, but we were not inactive. We were thinking about a follow-up of the task 67, task 40, because there are still remaining challenges. One of the challenges is the upscaling of production technologies for test materials. Another one is that we should work on the affordability and sustainability of test materials. What are the material requirements for novel test application fields like flexible sector coupling and Carnot batteries, because these are new fields in which the development for materials is not mature yet. Another challenge is how to translate the performance requirements into an optimal design of components. This is still a very difficult area. And the last challenge is that we should support the needs regarding test materials and components from companies active in this field. So there are a lot of companies active, and I think that we should work more on what are the specific needs in terms of materials, technology, or market developments to support them. So we have planned some new work, first on materials. We are planning to make more clear which lessons are learned on materials R&D, but also on application requirements, and disseminate then this actively and publish the best practices and lessons learned. Then on material characterization, We will include in the materials characterization already developed also high temperature materials for the new application areas, and work on new round robin tests for new materials properties. Then on material synthesis and materials production, work on the production upscaling methods, and work towards stronger commercial deployment of these materials. And we have a test materials database that will be filled more and expanded with available material data. Then the planned components work. In general, we work more targeted on component design, work on different design approaches, and on the parameters for appropriate design metrics to work on component and component design, and get more active feedback from practice. So active feedback from perhaps a round robin on component design and component testing, getting this back into the design procedure in order to improve the design approaches.
Wim, 20 minutes are over. Speed up.
Speed up.
Yes.
So work on state of charge, work on proof of concepts. We will work on applications and case studies, and also on the possibilities of artificial intelligence. That brings me to the conclusion of the work. Next steps that we will take for the follow-up that we will in April, so this month, have finalized the work plans. These will be discussed and decided upon by the executive committees, that we will have an official start of the work in July 25, and our kickoff meeting will be in October 25. For more information, see the last page. I also included a page with references for your perusal afterwards, and this will be ending my presentation.
Wow.
Thanks
Wim.
for your presentation.
Thanks, Wim. Great. Well, you have a lot to do still, even if you did already 12 years of research work within the IEA or something.
Indeed,
Great to see it, indeed. But exciting. Maybe we should say at this moment that there's always open doors for people who want to join the task. You should check in which country you are based, because this is a bit linked to the colored countries I showed in my presentation. And you can get in contact with Wim, which his contacts are on the website under task 67, and tell him what you want to do and how you want to, what you're interested in. That's the procedure.
Yes.
Perfect. Okay, very good. So let's go to our next speaker. We will have the Q&A at the end. So keep typing in your questions, and we make sure that we have enough time for the Q&A at the end. So we have Dr. Daniel Lager with us as the next speaker. He has been working in the field of thermal physics and thermal analysis since 2007 and is head of the Associated Accredited Laboratory of the IAT, Austrian Institute of Technology, since 2019. He has received his PhD from the University of Vienna in 2017, and he's also quoting his dissertation in his presentation, which is about the characterization of heat storage materials. Parallel to his work at IET, he is an external lecturer at the University of Applied Science, Burgenland in Austria. So, the floor is yours. I'm looking forward to your presentation.
Thank you for the introduction. So I will share my screen.
Yes.
So hopefully you can see it now.
Looks perfect. Super.
Okay, then let's start. So yes, hello everybody. My name is Daniel Lager, and I will give you some introduction into the material characterization of thermal energy storage materials and the used methodologies and techniques, which we also used in the IEA task, which Wim already mentioned. So let's start with the three technologies. I think Wim already discussed them a little bit, but from the material point of view, it's important to know that when we are talking about sensible thermal energy storage, we are talking about an enthalpy change due to the heat capacity of a material and the temperature gradient of the material. For the latent thermal energy storage, we are looking on the phase transition enthalpy or of the phase change material, as well as the transition temperature. And last but not least, for the thermochemical energy storage, we are looking on the enthalpy change due to some physical sorption, for example, or a chemical reaction. This is based on the thermochemical material. So these are the three different technologies focused on materials. But for all of these technologies, you need to have a detailed knowledge of the thermophysical properties of the material. And this is the presentation about. So here, a short sketch of the actual requirements of the materials. For example, for sensible heat storage materials, you want to have a higher heat capacity and a high temperature difference to store the heat. So you want to have also a high thermal conductivity, which leads to higher power, charging and discharging power of the material. And you also want to have a high density due to the compactness of your system. And when you look on the right side, you see here some material classes and the relation between the specific heat capacity of the material to the thermal conductivity. And as already expected, water has a really pretty high heat capacity, but a low thermal conductivity, for example, in comparison to metals. But when you look on the volumetric energy density versus the thermal conductivity, then you see that metals can be pretty attractive because they have a high thermal conductivity and you can store a lot of heat in a corresponding volume. So that was the reason for showing this graph. So this is about the sensible thermal energy storage. When we look into the latent heat storage based on phase change materials, there you want to have a defined phase change temperature of your material, and you want to have high phase change enthalpies. These are the two important points you want to know of your material, but you also want to have a so-called low subcooling, which means that the material is melting and crystallizing at the same temperature. And last but not least, again, a high thermal conductivity of the material to have fast charging and discharging of the material. Again, here on the right side, you see some comparison of different materials. For example, organic materials with a low transition temperature here, but also with a high transition enthalpy. When we go on the right side, we have here salts, for example, which have a high transition temperature to the molten phase and also high transition enthalpy. On the picture here on the bottom, you see the same materials again, but again, listed over the volumetric enthalpy change. And here you see, for example, that salts have a really high volumetric energy density at high transition temperatures in comparison, for example, to salt hydrates or paraffin waxes. Last but not least, thermochemical materials. So here you want to have a high enthalpy of the reaction or a high sorption enthalpy, depends on the material you're looking at. You want to have fast reaction rates, high thermal conductivity again for charging and discharging power. And this is the important point, the reaction must be reversible and stable for the application with the cycles you need, with the number of cycles you need in the end. Here on the right side, you see some of the known materials which are also in the literature. For example, when you look at physisorption, which can be a zeolite material, for example, you are in that range of the reaction enthalpy at lower temperatures. But in comparison, for example, to an oxidation reaction, you have higher temperatures and also higher reaction enthalpies. So this is just some introduction into the different materials and the quantities you need to know to identify if your material is good for the application you plan or not. So what are now the challenges in the measurements? When you measure these materials, you want to know, for example, the specific heat capacity or the phase change enthalpy. And for this, there is a typical methodology called calorimetry, in that case, differential scanning calorimetry, which is shown here on the picture on the right side. So you have a sample, you have a reference, and then you heat up both and you measure the temperature difference between these two. And this signal you get out of that, you see here on the left pictures. For example, here you see the specific heat capacity, the apparent specific heat capacity of a paraffin wax with a melting temperature at around 70 degrees C. So you have here the sensible part where you heat up the solid, then you get into the melting, and then after the melting, you're in the liquid phase. When you now look into the detail of this curve, so this is a focus of this temperature range, you see here high uncertainties because of the heating rate you use in the system. When you use faster heating rates, which is shown here in the pictures below, you see here that this peak is broadened and the peak height is lower, but the uncertainty here is much lower. And the idea of these two, or the comparison of these two measurement procedures, shows that you cannot use every procedure for every quantity. For example, I would not use this procedure to analyze the specific heat capacity because the uncertainty in that region is pretty high. So for specific heat capacity, I use fast heating rates to identify the specific heat capacity. But if I want to analyze a temperature where the phase change occurs, like here at 70 degrees centigrade, I would use lower heating rates to get a better temperature signal in comparison to faster heating rates. This should show the influence of the heating rates in calorimetric measurements. For sorption measurements for thermochemical materials, you also need to know the water vapor or the gas phase you want to apply on the material, and you need to know the pressure of this gas and also the temperature. For example, for sorption materials, you need to identify the so-called desorption temperatures and sorption temperatures. In that case, you see that between 230 and 40 degrees centigrade. And out of these procedures, you can then identify the so-called sorption isotherms. So how much water or gas phase is uptaken by the material, and what is the relating enthalpy of this sorption process. Here you see an example for a zeolite. This is a zeolite you see here. These are pellets of a zeolite 13X. And we measured with that, with a so-called thermobalance, the uptake, the water uptake, water vapor uptake at different pressures. And this is shown here in this graph. So here you have on the x-axis the pressure of the water vapor, and on the y-axis the water uptake. And you see the higher the pressure is, the more water uptake I get. And this is one result you can get out of this gravimetric sorption measurements. Additionally, you can also get the so-called kinetics. So how fast is the gas adsorbed or desorbed in this process. So another point or other important thing to know is the so-called thermal diffusivity and thermal conductivity. And why this is important, especially for packed beds, as you have it for thermochemical materials, is the influence of the gaps in between your, for example, of your powder or your TCM material. I show you here some example with, this is an yttrium stabilized zirconia, so it's a ceramic material. But we measured here the thermal diffusivity with different gases. And you see here at ambient conditions, the thermal diffusivity is higher than when I measure under vacuum conditions. So in that case, it really depends on the gas phase between the particles. When you look on this graph here on the right side, you see what it's the influence of helium in the same measurement. So we did not change the sample, we just changed the gas phase. So the so-called effective thermal conductivity strongly depends on the gas phase you have in your system. Here's another example where we measured the same material with a so-called heat flow meter, which is also a possibility to measure the thermal conductivity through the packed bed. And you see here the dependence also of the thermal conductivity depending on the packed bed density you have or bulk density you have. So also the packed bed density and bulk density strongly influences the thermal conductivity, the effective thermal conductivity of your measurement. So that was the more or less to show you the challenges in the measurement. Now we'll come to the results of the last IEA task 67, where we had a subtask on the material characterization. And I think Wim already showed us the motivation. So the idea is to have the international collaboration of experts in material research, and that we get more or less reliable and reproducible data on the characterization of test materials, and to harmonize the measurement procedures for that. And we did that with different measurement systems and different measurement quantities. One of the quantities was the thermoconductivity and diffusivity. Here we had 3 different systems. Eight different methods we compared to each other, and we measured a paraffin wax with a melting point between 53 and 58 degrees centigrade. You see the material here, and the main 3 methods we were looking at was laser flash, hot wire, and transient plane source techniques. And I show you here one result of the laser flash output, or of the laser flash round robin. And the interesting thing was that we get comparable data, but although we have the same procedures, we still have some issues with the same sample preparation and sample preparation procedure, because the sample preparation can strongly influence the results of the thermal diffusivity measurements, especially in the laser flash. So what we found out here, that it was really challenging to identify the procedures also for the other systems and for the other methodologies. And what we've also seen, that the approach of the assessment of the uncertainty is strongly dependent on the labs. So all the labs use different approaches to define the so-called measurement uncertainty. And one point also of this task was to harmonize this assessment of the thermal of the uncertainty approach. For specific heat capacity of powdery materials, we also looked at 3 different materials. It was a strontium bromide, a hexahydrate, and a zeolite 13X. And here we defined the procedures for the calibration, for the systematic baseline runs. Baseline runs means the systematic deviation of the system itself. Then measurements with reference materials. We harmonized the sample preparation. And then we did also a harmonization of the specific heat capacity evaluation. Here is one example of the specific heat capacity of strontium bromide, where you see that worked pretty good, although the uncertainties are strongly different between the different labs. For the anhydrous material from the strontium bromide, we get really comparable results. Where we have seen problems is when we have hydrated materials. So if we have different hydration states, or if we have water in the sample, then the results were stronger deviating. So, and the reason for that, we see again in the sample preparation, to really have the same hydrated material in the measurement system. For sorption enthalpy, we looked on gravimetric system. Here we defined a standardized procedure where we desorb the material at 350 degrees C. It was again a zeolite 13X. And then we just measured the equilibrium at 95 degrees centigrade at a defined water vapor pressure. Then we adsorbed from 95 degrees to 35 degrees C, and then we desorbed. And the idea was to get here a comparable, so an easy procedure that different institutes can follow that pretty easy to measure that. The problem we had here is that we just had 3 institutes measuring this material because of problems with the devices, or not the possibility to set up the device in a manner that it can follow this procedure. So for the future, we have to focus on enlarging the number of labs to also involve other apparatuses under a more simplified protocol. Nevertheless, the 3 participants showed their data, and we have seen, okay, we had two participants which were really comparable. One participant was a little bit off, but for the future, to have really a statistically significant result, we need more participants for this kind of round robin tests. Yes, then the 2 last quantities I want to show you is the density. So for density, we also use the same paraffin wax as I've shown you before for the laser flash system. Here we measure the density in the solid phase and in the liquid phase with 4 different methodologies. So computer tomography, oscillating U-tube, Archimedes principle, and pyknometer. And the interesting thing here was that we have seen that we all get really good results in the liquid phase, but in the solid phase, we have strong deviations. And due to that, we developed, especially for the Archimedes principle, a new approach or a harmonized approach to do it in the next task, again, a round robin with this harmonized approach to get more comparable results for the density. Last but not least, viscosity measurements. For the viscosity measurements, we also used the same paraffin wax, but we additionally used the standard oil so that we also have a reference material in the round robin test. And here we measured with a shear sweep measurements. So geometry was defined, the times were defined, and also the temperatures were defined. And here we get really good comparable results for the paraffin wax. What we have to do in the future, or what we want to do in the future, is to also measure other PCMs, so not only paraffin waxes, but also other materials. And we will also want to look into non-Newtonian materials to adapt these procedures and to do also new materials in the viscosity measurement. So these are the outlooks or the plan for the next round robin tests in the IEA SHC task. To conclude, so what we have seen is that the characterization of the test materials requires new measurement procedures, not always, but depending on the material, we have to look at it. And it's not too easy to measure these properties in a comparable way. So it's really important to identify new procedures, new measurement methodologies to assess these quantities. And I think the IEA task enables this international comparisons and is allowing us to harmonize these procedures. Okay, so that's all from my side. I hope this was interesting for you. Thank you for your attention.
Wow, Daniel, very nice. I think it really shows that there was substantial work being done within this last task, and really, yeah, impressive. And the harmonization still needs a lot of round robin tests to make sure that all tests are testing the same things.
Yeah, correct.
Well, is my screen now visible? That looks a bit different than before.
Not yet.
Not yet. Okay, that's why this button doesn't work. Let me check. Yes, I want to present the next and last speaker, and we'll take my presentation from here. Here we go. Oh no, this was wrong again. Yeah, it's Christoph Radberger, our last speaker for today. He is Deputy Head of Thermal Energy Storage Group at the Bavarian Institute of Applied Energy Research in Germany. His main field of research are phase change materials based on salt hydrates. As part of several working groups within IEA SHC, he has investigated experimental methods for characterization of PCM under application conditions. So, Christoph, I'm looking forward to your presentation.
Thank you for the kind introduction. I will share my screen. Okay, here we go. So the starting question of my presentation should be how to determine and categorize materials performance degradation. And with materials, obviously, these compact thermal energy storage materials are meant. So here you see the outline. I would first like to introduce to you the effects that stability of PCM and TCM influenced. Then I would like to talk about what is reported in scientific literature and what is missing. Following this, we'll have a look at investigating degradation under application conditions and mapping degradation. So those were the activities in the task 6740. And to end with summary conclusions and a list of references. So first point is the stability of PCM. And as you have heard, we are using different materials as PCM. Most of them undergo a solid-liquid phase change. So in applications, PCM are thermally cycled. As you see here, you have the transition from a solid material to a liquid, and then vice versa back to a solid. So the takeaway is that the main process that affects the degradation of PCM is the temperature change and the change of the phase from, in most cases, solid to liquid. Examples for the degradation of PCM. There are many more, but two very common examples are first, for organic materials, a chemical degradation at high temperatures. So you see the picture on the left here. It's a sugar alcohol, mannitol, that was exposed to high temperatures in the liquid phase under air as atmosphere, and you see something like a browning of sugar, which is not wanted if it's applied as a PCM. A second example, and this is observed for mixtures of PCM or salt hydrates, where you can see a phase separation. So during repeated thermal cycling, you can observe that different components of the mixture, and solids and or liquid phase, they separate from each other and do not homogenize again. So what affects now the stability of TCM, thermochemical materials? Again, different material classes and also composites are used as TCM. So the stability of PCM is a question of the material class again. At the bottom, you see some examples of the synthesized materials the experts of the task are working on. And now in applications, TCM are subject to heat and mass transfer processes. So in comparison to PCM, we have also a mass transfer, for example, of humidity to and from the TCM sample. So this also leads to processes affecting the stability. And here are some examples for the degradation of TCM. We already heard a lot about zeolite. So zeolite is typically used in pellets, in beads, or composite. And during hydrothermal cycling, so at elevated temperatures and humidities, you can observe a breaking up of these pellets or composites, which is, of course, unwanted. And you can also observe a transformation of materials that were crystalline at the beginning into an amorphous phase, again, leading to a change in the water uptake or a change of the reactivity of the material, thereby reducing the energy density. So that's for the examples to start. Now, the question that we asked us in the task was where to contribute. So what is reported in scientific literature, and you'll find many papers out there. Here's just a selection of 3 that somehow give an overview of the state of the art. So you'll find many review papers on tested materials and the corresponding applied testing methods, papers on thermal cycling of PCM, and then you see the number of cycles carried out and so on. You see papers that work on methods to test, or here's called validate, storage materials. So with validation, here the idea is to have reference application conditions and test the materials accordingly. And then there's a third paper as an example where a systematic approach to investigate property degradation of PCM is presented. On the following slides, I'll give some more details, but of course you're welcome to check the references and have a closer look by yourself. So the first example was by Bayon and Rojas. They proposed a method to validate these materials And I would like to cite one of their statements. They say that no testing protocol or guideline exists for validating storage media. And the reason or the consequence is that the authors apply their own criteria for designing testing procedures, but also for predicting the material behavior in the long run. So, and then they conclude that to perform accelerated tests, it is crucial to know the relevant degradation factors. They can be high temperature, oxygen, atmosphere, and so on. And then to perform tests under an increasing level, stress level of degradation factors. Next paper presented by Mehling, an approach to investigate property degradation of PCM. Again, here I like to cite one statement. So as different applications impose different conditions, testing should be tailored to the individual case. This sounds pretty straightforward, but it's a very, I would say, very important statement here, because that should really be the starting point for material degradation studies. And he proposes as a first step to identify the basic functions and the related properties that might be subject to testing, for example, with a specific application in mind. So the question is now, what is missing in scientific literature and what could the task experts contribute to our understanding? Material class specific information was missing on the classification and differentiation of the relevant degradation mechanisms. Suitable test methods to investigate degradation under application conditions are partly missing or partly not indicated. And then it would be good to have recommendations for procedures to accelerate degradation in order to speed up degradation tests. Now coming to investigating degradation under application conditions. So this is, let's say, the approach that we are following in the task for many years. What do we mean with application conditions? So usually measurements are done in the lab. For example, these measurements of thermophysical properties Daniel has reported on. They are performed in the lab environment. And then on the other side, we apply the materials and a thermal energy storage unit as part of an energy system in a so-called application environment. And obviously, we cannot do the material tests out there in the application environment. So we have to somehow translate the application conditions to the lab, and that leads us to measurements under application conditions. If you're interested to find out more about this approach to investigate under application conditions, there was a paper from the previous task phase on experimental devices to investigate the long-term stability of PCM under application conditions. And on the right side, you see a screenshot of the many various techniques and devices, also self-built apparatuses that the experts deployed to investigate their PCM materials. Now coming to the main part and also the main outcome of the degradation work in task 67. So we called it mapping degradation. What is it? So we would like to provide an overview of the relationships between test conditions, the degradation mechanisms, the effects on the storage material, and also the effects on the thermal energy storage system. And following this, would like to give some recommendations for accelerated degradation testing. So the guiding questions were, what are the reasons for degradation on material level? What are the effects of degradation on the material properties? Then how to identify and quantify degradation, and again, how to accelerate degradation to achieve fast testing. And this mapping, we proposed and discussed several approaches during the task phase, and I will show you two examples of the degradation mapping tables or slides. So the first approach looked like this, to have a everything at a glance. So here you see it's an example for sugar alcohol used as PCM, studied by CMAT. So they filled in their expertise on the degradation of this sugar alcohol, or the stability testing of this sugar alcohol, with a conclusion on the overall stability of the material, then on the effects that influence stability. So stability might change with, as you see here, the time under service conditions, so time under high temperature, melting freezing cycle. Then they said that stability might change due to basically two processes, chemical reactions or evaporation. Then attached to this, the question of what are the properties to look at to investigate these two stability and degradation processes, and also giving a bit of a background for the reasons to better understand degradation and possible measures to avoid degradation. So this was a way of illustrating this mapping degradation on one chart. A second approach was then proposed. Here you see a scheme of the tables that were prepared by the experts. So the starting point for this approach are the degradation mechanisms, what we call, that's, for example, phase separation, corrosion, polymorphism, evaporation, chemical degradation, and so on. Then it's important to link these degradation mechanisms to the degradation factors influencing them. So that's the boundary conditions or the testing conditions, like temperature, thermal cycling, the type of atmosphere, et cetera, et cetera. And the next step, we are, of course, then interested in the effects on the material that the different degradation mechanisms have. And this is categorized in change in transition, enthalpy, temperature, thermoconductivity, and so on. And finally, if tested, we are also interested in the effect of the degradation that are observed on the system level. Usually you measure the thermal power, storage capacity, and the degradation then will lead to a change in these in the system performance. Now I would like to give two examples, one for PCM fatty esters. You see here the table. Just to pick one, we have different degradation mechanisms that were tested for fatty acids here. One, for example, is the chemical degradation. So the first line, chemical degradation, depends on mostly on the temperature. And if the chemical degradation occurs, then on material level, you will see a very high effect on thermal conductivity, on the enthalpy, and you will observe a mass loss. And now you see these different effects on material level. For example, if we look to effect number C, enthalpy decrease, that will then in turn have an effect on the performance of the test system, for example, on the test capacity. So you also see a direct contact latent heat storage system was tested by Lucerne University of Applied and Arts. And in addition, there are some recommendations how to test and accelerate the relevant degradation mechanisms and how to deal with degradation. So for the example of chemical degradation, that would be ester bond breakage that can be tested with thermogravimetric analysis. And well, here it's quite obvious how to deal with that. Higher temperatures above the degradation point should be avoided. A second example, a TCM, a potassium carbonate. You see again the table, and well, these particles, we have seen pictures of TCM pellets and beads before. So one degradation mechanism is the agglomeration of the particles, and this is strongly correlated to thermal cycling as degradation factor. So repeated heat and mass transfer to or from the potassium carbonate sample and particles leads to accumulation. This in turn leads to an enthalpy decrease on material level, and this then affects, well, basically the enthalpy decrease affects all of the properties that here were measured for a fixed bed packed reactor. So power, efficiency, capacity, all are affected by difference on material level. And a way to counteract, to deal the degradation here, could be the stabilization by making composites of the potassium carbonate. So to summarize and conclude, or maybe to start with the definition at the beginning, we can say that PCM and TCM are stable if their properties remain within a certain limit. So properties of interest are, as you see here, melting, reaction enthalpy, chemical composition, transition temperature, and so on. So the material stability of PCM and TCM highly depends on the nature of the material, so the material class, and also, of course, on the operating conditions of the application or the applied laboratory testing. And that means that general statements of the type material whatsoever is stable or the material is not stable, they should not be made without reporting the testing conditions. We see that understanding the stability of CTES component and system level, that this starts with the degradation processes on material level, so on the very basic material research level. And then we worked on stability mapping, and this offers a useful visualization of CTES material degradation behavior. And we also talked about experiments to accelerate degradation, and they can be recommended to speed up stability investigation. Well, so to end with a positive statements, we also have to say that in many cases, really many cases, operating conditions can be selected that allow an application without a performance reduction caused by material degradation. Here you see the list of references included in the presentation, and with that, I'd like to thank you for your attention.
Yes, thank you. This was a great recording. I hope you all enjoyed it. It was a full range of a lot of different topics, very research oriented, but very important material science for our improved compact thermal energy storages. Now I am here with the speakers and we will have a live Q&A. They are all here. Hi, everybody. Good morning. And
Morning.
great to see you.
Morning.
Yeah, we have already some questions, and I would like to start straight with one question that was raised also in the other webinar, which is concerning the hidden champion sort of sodium acetate trihydrat SAT. Can you say a word on that, why this is used a lot and whether it could be a suitable material?
Could I
You
start?
can-
And then
Okay.
maybe you can jump in. So, well, it has very good material properties, comparably high energy density at reasonable costs. Also handling in terms of safety issues is no concern. So it's a very good material, but the only one thing is that it melts at 58 degrees C. So suitable for applications where the 58 degrees C are useful, but for others you need other materials, and that's why the community works on so many different materials, because especially, well, PCM need to be tailored to the temperature range of your application. You can, of course, modify SAT a bit. You can go to mixtures with SAT and other salts, changing the melting temperature a bit, but there are limitations to apply SAT in other fields, I would say.
Okay. Daniel, you want to also add to that for your big range of materials that you observed in your PhD?
So I think you cannot say one material is now a good one or a bad one. It really depends on the application. So finally, as Christoph said, it's depending on the transition temperature you want to reach, and it's dependent on the enthalpy and also on the power you want to reach. So on discharging or charging power. And this is strongly dependent on the thermal conductivity. So I would not prefer any material. I would just say there are materials suitable for some applications and for some applications not.
Okay. Danielle, you were also asked, the question is relying to heating rate, how to choose the heating rate for different PCMs.
So I think the question is focusing on characterization. So when you measure, for example, calorimetry with DSC, so you use a DSC for measuring phase change materials, it strongly depends on what you want to see. If you want to measure temperature accurate, so you will choose low heating rates, because then the thermal transport processes can be neglected in the sample. If you want to evaluate the specific heat capacity of a solid or a liquid phase, you need to use higher heating rates because of the sensitivity of the system. The higher the heating rate gets, the higher the sensitivity gets, and the more accurate the results get. So it's, again, strongly dependent on what you want to measure. Yeah.
Okay. I think this could be also a question to you. What makes PCMs have different phase change enthalpies and temperatures in general?
Yeah, it's mainly a structural question. So a good example, I think, are polymers. When you melt or crystallize polymers, then it strongly depends on the thermal history of the material. For example, when you crystallize a polymer from the liquid phase to the solid phase, and you leave or you use very, very slow cooling rates, the material has a long time to rearrange. So the structure and the entropy is getting higher and better. And when the structure is getting better, then the melting enthalpy is getting lower. The more unstructured your material is, the higher the melting enthalpy gets. So that's the difference in the enthalpy you see, for example, in polymers.
Okay. Another question to you. It says, since the quality was not so good, can the information about 13X and other sorption materials you showed found in some paper or publications?
Yes, I strongly recommend the NIST database on sorption materials. So there is from the National Institute for Standardization and Technology in the US, a database called the ARPA database, where you find a lot of different sorption materials and their uptake properties and sorption isotherms. So I can really recommend that.
Okay. Christoph, we have learned in the recording that you were involved in the dishwasher development, and we have questions here talking about where PCMs and TCMs are really used in already in kind of products. Can you say a bit more on that? Which temperature range is it with material and cycling resistance and all that?
Well, in the dishwasher, it's a TCM, it's a sorption process using the zeolite. And this is, as you already said, commercially available on the market for many years. Besides, yeah, I think we also had this question in the first Q&A. So we see that there is a commercial system, for example, again with the sodium acetate trihydrate by some companies on the market for domestic heating or domestic hot water applications. And then we see the commercial systems where especially PCM are used to stabilize temperature sensitive goods like pharmaceuticals or bioactive materials. And we see And this is maybe not the type of materials we were discussing today, but we see, of course, a lot of companies and a lot of installation on ice storage systems. So water ice, a very traditional PCM, but still a very interesting application, very good properties of the material, and of course very good economics, because water and ice are rather cheap. So and these both the ice storage systems and also the SAT systems, they usually work together with heat pumps, so that's a good match for PCM to have a latent heat storage as a source for the heat pump.
Okay. I think there is also this open field that Wim stressed in its outlook for the next task, which looks into higher temperature materials. To which extent has the task already generated results on that, which PCMs, TCMs could be suitable for, let's say, above 150 degree, and what is necessary there still, Wim?
There are a number of groups that already are working on TCM and PCM for higher temperatures. The reason that we incorporated the higher temperatures is also because of the two new, say, application areas from Carnot batteries, in which you store electricity in the form of heat and then use the heat later to generate electricity again, is one of the areas. And the other one is the direct electrical heating to store, so the power to heat, to store electricity for later use as heat in, for instance, industrial processes or for district heating. And we saw that there is still a need for more uniform characterization and uniform key performance indicators for materials at that high temperatures. And that is why we included this into the work of the future task.
Okay. And Daniel, from your point of view, you showed graphs where there were already materials at a higher range. What do you recommend? Which are your hidden champions?
Yeah, I think we should also look into metals like, for example, aluminium, because they are pretty cheap. You can also use recycled aluminium. You have a melting temperature at around 600 degrees centigrade. So it could be a good application, for example, for CSP or other applications. So I think there are a lot of possible other high temperature candidates which are pretty cheap and also have good physical parameters like good thermoconductivity and high melting enthalpy, like aluminium.
Okay. We have actually a challenging question here, which asks us why not just use sensible heat storages, because water is the most easiest and can be heated up directly by different sources. All the other materials proposed in the presentations are more expensive and more impractical. This person says, why not just use water for sensible heat storages? Why are you doing your research?
Yeah, then there are two main reasons, I guess. The first reason would be a volume limitation. So water has a given volume, and for those applications in which there is a smaller available volume, then alternatives are good. And the other is the temperature range. So between 0 degrees and 120 degrees or so, water storages can be very efficient and also economical viable. Above those temperatures or below those temperatures, we need other materials. And that is, say, these are the main exclusion factors for water, I guess. But indeed, water is a good champion at the moment.
You others, you want to jump in?
Yeah, maybe it's a bit of repetition, but you have some additional benefits for if you use other PCM. You have this temperature stabilization. We already talked about that. That can be an additional benefit of a latent heat storage system, this passive temperature stabilization. And then TCM, so many TCM, actually they work a bit like a heat pump. So you can transform the heat that you discharge from the storage, you can transform it temperature-wise. So this can also add flexibility to your energy system. And I would say that the most attractive compact thermal energy storage systems are those where you utilize these additional benefits. But for many other applications, water is a good material, and it's of course already used. Yeah, so
I saw some examples where, where the trend on the ISH, the big Frankfurt fair, it seems that they offer heat pumps, including compact energy storages, as a wardrobe sort of size thing, that you could put into your hall in your flat even, because it's just a furniture sort of. So it's a very compact thing, and there is the compact storage in the bottom, and there is a heat pump on the top, and this gives you a very, well, space-consuming way of heating hot water or your building. So that could be also
and that's a good way to do it, because then you also have in the planning phase the storage and the heat pump together as one component. That
they
definitely
correspond
makes
very
sense. Yeah, to have
nicely.
some control of that, and yeah, can really optimize both components to each other.
Yeah. Christoph, there's another question to you. Can you give more information after the webinar about sugar alcohol research of CMAT, if I understand right, in form of a public paper? Will there be something coming?
Yeah, there's already literature published by CMAT from Spain on that topic. I could share the links, yeah, but the question is to whom? I can see it in the chat, or?
Well, I don't see. What do you see the questions?
I see it. I can connect you. No worries.
Okay.
Arabella is very good informed. Okay, so that would be nice. And Daniel, regarding your heat rates, there's another question, or the follow-up question. Slower heat rates means 1 to 10 Kelvin per minute, and higher means above 10 Kelvin per minute. How do you classify slower and higher heating rates? Oh, we lost Daniel?
No, I'm here. I'm here, still here.
Sorry. Okay. No, I think I narrowed my screen. Yes.
Yeah. So the heating rate, you can just measure by changing the heating rate in your experiment. So for example, if you see still changes in the phase change when you lower the heating rate step by step, then you can go lower until you won't see any changes anymore, because then you get rid of the thermal transport properties. Higher heating rates means above 10 kelvins per minute, yes, but it also depends on your device you have. For example, in our device, we can go up to 50 kelvins per minute for fast heating rates. But you have to be sure that you're in a let's call it dynamic equilibrium. So in a constant heating rate for your evaluation. So if you heat too fast, then the time until you reach this equilibrium takes time. So yeah, I think above 10 Kelvin, 20 Kelvin, 30 Kelvin per minute is higher heating rates for classical heat flow DSC, and 1 Kelvin or below 1 Kelvin is better for temperature accuracy measurements with a classical heat flow DSC. I just want to add some point to the water storage, because I think this is also interesting for the people. In Finland, there is at the moment one of the biggest water storages built, or it's just in construction. It's called the Varanto, the largest cavern thermal energy storage, which will be filled with water, with 1.1 million cubic meters of water, and with a capacity of 90 gigawatt hours to heat the district network in Finland. And they use, for example, temperatures up to 140 degrees centigrade, with the water in this cavern thermal energy storage. So this is also under pressure, this system.
Wow.
And you can look it up. I think it's pretty interesting, and it's very interesting for district heating missions.
Yeah, I assume that district heating and compact energy storage is usually not an issue, because the quantities of heat you have to store are very big. I think compact thermal energy storage has really come in place where, well, room and space is expensive, like in flats or even industries or something.
Yeah.
Okay, good. I think there are no more open questions. Do you have anything to add from your point of view?
No.
All fine. Okay. So we encourage all participants to get in contact directly with the speakers if there are any more technical and more detailed questions, and join the new task if you are also in the field of research, and contact Wim, because there is a new task, as we heard, coming up, and this is always a good chance to group in and join and network with other researchers in this field. I think you formed a very, very wide and very effective research platform with your tasks. So I hand back to Arabella and thank for hosting this webinar again to ISIS.
Yes, thank you very much, Bärbel, and thank you very much to all of our speakers. Just a few more information before we close out for the webinar today. There will, of course, be a recording of the webinar that we had just heard now, and it's going to be made available to you via the IEA SHC homepage and also the ISIS homepage. For any ISIS members on the call, remember you have unlimited access to all recordings in the ISIS members area. And then there's big news to share from ISIS's side. We are hosting again our ISIS Solar Work Congress. This year we're going to go to Brazil. It's going to take place in early November from the 4th through the 7th. Our abstract submission system has opened. We are now accepting your abstracts. So in case that you are interested to present your latest research, do join us in Brazil. It's going to be quite an event. It's going to take place just a few days before COP is going to come to Brazil. So the whole of Brazil will be a buzz, and it's going to be a great platform to share your research. The deadline for abstract submission is the 30th of April, and you can learn more on our homepage, www.isis.org. And with that, thank you very much for joining us on the call today. You can stay in touch, of course, with both IEA, SHC, and ISIS on different social media platforms. If you have any questions, you can reach out to us at public.relations@isis.org. And we are very much looking forward to seeing you on the next webinar. Bye, everybody.
Have a great day.
Bye-bye.
Bye-bye.
Thank you.
Thank
Bye.
you.